For all of our other discussions on confidence intervals, we've been trying to find the confidence intervals of the population mean, or mu, and the population proportion, or p. And both of these values are distributed normally with some mean of mu and some standard deviation of sigma. So those are both normal, mean mu, standard deviation of sigma. However, what if we want to try to find the confidence interval for another parameter? For example, the variance, so sigma squared. If we're trying to find the confidence interval for sigma squared, since sigma squared is not normally distributed, it's instead a chi-square distribution, where this funny little x value is called chi, and the chi-square distribution, we need to use a different formula and a different set of tables to be able to find that type of confidence interval. The chi-square distribution, which similar to the student's t distribution, is based directly off the degrees of freedom, whereas for the student's t distribution, the degrees of freedom simply stretched and constrained the normal distribution. The chi-square distribution has some interesting properties that you can see over on the right, where the degrees of freedom will drastically change what the distribution actually looks like. And to create the confidence interval for our sigma squared value, we have the following formula. We have n minus 1 times s squared over our chi-squared value at alpha over 2, and then that is less than or equal to our sigma squared, which is then less than or equal to, again, n minus 1 times s squared, and that whole quantity over chi squared at 1 minus that alpha over 2 value. So 1 minus the quantity alpha divided by 2. So now we're going to try to use this to find the confidence interval for a specific variance. So for our example, we're going to use a sample size of n is equal to 10, which means our degrees of freedom is equal to n minus 1 or 10 minus 1, so that's equal to 9. And then we have our sample variance, s squared is equal to 5, and we're going to be looking for a 95% confidence interval, which means our alpha is equal to 0.05. So to start off with our formula, we have n minus 1 times s squared over our chi squared at alpha over 2, so 0.025 with 9 degrees of freedom, and that's less than or equal to our sigma squared, which is less than or equal to, again, n minus 1 times s squared over our chi squared value at 1 minus that 0.025, so 0.975, and again with 9 degrees of freedom, so we have a 9. So if we fill in our values for that, we have 9 times our s squared value of 5 on both sides, and then they're divided by, we have chi squared of 0.025 with 9 degrees of freedom, and if we look that up on the table in the back of our book, we get 19.0228 on the left, and on the right we have chi squared of 0.975 with 9 degrees of freedom, which gives us 2.7037. And if we do that, we multiply out both sides, we have 45 divided by 19, and we have 45 divided by 2.7. We get our confidence interval for our variance of 2.3656 less than or equal to our variance, sigma squared, less than equal to 16.6644. And that's how we calculate our confidence intervals for our variance with that simple formula.